In this lesson, we're going to take a look at expanding and simplifying polynomials, which is something you've done several times before. So most of this should be review, hopefully, but usually it's a good idea to brush up on this stuff before we continue into the slightly more difficult parts to make sure that we understand what it is we're doing and how to do it. So just a little quick review from the last lesson. When we multiply two powers together that have the same base, so for instance, if I do, let's say, x to the exponent 3 times x to the exponent 5, it says that we keep the same base, and the exponent is just the sum of the two. So 3 plus 5 is 8. Or in general, x to the m times x to the n equals x to the m plus n. So let's just try a couple of these quickly. 3 plus 5 is x to the 8. Second one, we've got our coefficients there. We treat them separate from the actual powers of x. So we just do 7 times negative 4 is negative 28. And then we've got x to the 4 times x to the 5th, so we add exponents x to the 9th. This one here, we've got to do the exponents outside the brackets first. So the first one, negative 5x all squared, really means negative 5x times negative 5x. Well, negative 5 times negative 5 is 25, and x times x is x squared. And similarly, 2x all cubed is 2x times 2x times 2x, which is 2 times 2 times 2 is 8, and x times x times x, which is x cubed. 25 times 8 is 200. The power keeps the same base. We add the exponents. 2 plus 3 is 5. If you'd like, you could pause now and try some of these on your own, or we just keep going, whichever your choice. So for this one, add exponents. 2 plus 4 is 6. Multiply the coefficients. Negative 2 times negative 3 is 6. Keep the base on the power and add the exponents. 3 plus 6 is 9. We've got 3 together here. That's okay. Negative 4 times 6 times 1 is negative 24. X squared times x cubed times x is x to the 6. And the last one, I think these are pretty much, if these aren't the same we did in the last lesson, I think. X squared times x to the cubed is x to the 5th. Y6 times y is y to the 7th. Okay, so there we're kind of done our little review from the last lesson. Moving on, let's combine some like terms. Most people have no problem with this one, although I still have students even in the senior grades that forget what happens when you simplify terms with the variables. A lot of people will take a variable and square it or cube it or do some other weird things with it. Like terms just means that we have two things separated by pluses or minuses and that they have the same variables with the same exponents. Now on the first one, 5x squared plus 2x to the 5th, actually x squared and x to the 5th are not the same terms, so we can't do anything with this. We actually have to leave it like that. There is no collecting of like terms in that problem. And sometimes that happens, and that's okay. It just means that we've already collected all the like terms we can. For part B, we've got 5x squared. We've got plus 3x minus 8x plus 7. The only two terms there that have the same variable with the same exponent are the 3x and the minus 8x. So we'll just include the other terms as well. 5x squared stays the way it was. And by the way, it's never a bad idea to underline these as you go, especially when there's several terms, just to make sure that you don't miss any. 3x minus 8x is negative 5x, and then plus 7 at the end. Now for these last couple, we've got a lot more terms, so we should make sure that we're not missing any by underlining them. 3x cubed is the only x cubed term. We have 3x squareds. That's the only x squared term. Minus 2x plus 7x is plus 5x. And plus 4 minus 9 is minus 5. So there's all the like terms that we can collect for that particular polynomial. This one, Okay, we're starting off with a 3x squared y. Do we have any more x squared y's? And I don't see any except this one here is a yx squared. And even though the order is different, it's just multiplication. Multiplication can happen in any order we want. So x squared y and yx squared both mean the same thing, so we can put those together. 3x squared y's plus 6yx squareds is 9x squared y's. And technically I could have put down yx squared, but for final answers I always like to put things in alphabetical order just so we have some consistency. Similarly, here we have 2xy's and 4yx's. Either way, that's the same. That's 6xy's. And this one, there is no other x with a y squared, so it's its own thing. And I'm just going to switch the order again to be alphabetical. So 5xy squared. Okay, so again, just to collect like terms, they have to have the same variables with the same exponents. And we don't do anything to them once we've collected them. We don't square the result. We don't cube the result. We just leave the variable the same with the same exponents that it had when we put them together. The distributive property, this is just a fancy way of saying we're going to multiply a polynomial by something, in this case a monomial or a single term. And we remember that it goes to each term inside. So a times b plus c is a times b plus a times c. Everything in the bracket gets multiplied by the thing in front. All right, let's try just an interesting word problem that kind of uses this idea. A football field has dimensions of 110 yards by 65 yards. Write the equation of the perimeter of the field. So the perimeter, if you think about the field like this, we'll just do 110, 65, 110, 65. Whenever I'm doing perimeters, I like to go around the outside and just make sure I don't miss any sides. So 110 plus 65 plus 110 plus 65. Or you could have written that as 2 times 110 plus 2 times 65. 2 lengths and 2 widths. Now use the distributive property to write this in another way. Yeah. We could write that as 2 times, I'm actually going to do the distributive property, I think, backwards. 110 plus 65. So I think you'll notice that if I did this, I would end up with that and that. So those are just different ways of writing it. And then you choose which method you want to use to find the perimeter of the field. I think I'll use the last method we did. 110 plus 65 equals 2 times 175 equals 350 yards in this case. Okay. Expand and simplify the following. Now these look a little bit messier. I'm actually going to make them a little bit bigger on the screen just so they're easier to see. But they still follow the same rule. We multiply that times that and that times that. Now when we do that, 3 times 4 is 12. X squared times x squared is x to the 4. Y times y squared is y cubed. And then 3 times minus 7 is negative 21. X squared, x cubed is x to the 5th. And y times y is y squared. And I could check to see if there's like terms, but if there were no like terms in the bracket before, there won't be any like terms in the brackets after. Similarly for the other one, got to make sure we do everything in the bracket, each term in the bracket multiplied by the thing in front. This will give us negative 6 x to the 5, y to the 5, plus 12 x to the 6, y to the 6. Okay, so that's pretty much old school stuff, as is the next thing, but this one at least is a little bit more interesting for us, and that's multiplying binomials. So some of you may have learned this as something called FOIL, first, inner, outer, last. first, outer, inner, last. Just making sure I actually do the FOIL order. But you can call it just the distributive property for a binomial times a binomial, which gives you the AC plus AD plus BC plus BD in general. Now I'm going to show you something called the box method. You can use it or not. Both of these methods work just expressing it out algebraically like it is right here. The box method, I find it's harder to make a mistake. It's harder to goof on something. And so what we're going to do for the box method is just make a little rectangular box. You can make it as big or as small as you want. I'll just make it big enough that it's clear on the screen for now. And I'm going to break it into two pieces. And I'm breaking it in a way that I don't want it to look like it's in equal quarters. I want them to look like they're all kind of slightly different sizes, give or take. They don't have to be, but they can be. And I'm going to think of this as the area of a box, which is length times width, and it's broken into 4 separate boxes, each of which has an area of its length times its width. But one of the two things I'm multiplying is A plus B. So I'll think of A as that length and B as that length. And likewise, I'll think of these as C and D. And then the area of each piece, well, this one would be A times C. This one is B times C, A times D, and B times D. And if I add those 4 together, I get AC plus BC plus AD plus BD, which if you check above is the same as the original formula. The terms are in a slightly different order, but the order of terms really doesn't matter. Now, to be clear, if you like the box method, use it. If you don't like it, don't use it. What I will say is that if you ever have to do anything bigger than a binomial times a binomial, like say, for instance, a trinomial times a quatrinomial, which will end up having 12 terms, the box method really helps ensure that you don't miss any, whereas the algebraic method, you'd be surprised how many people miss an arrow or double an arrow or something like that. But the box method makes it almost foolproof. Okay, so here we have a rectangle, and we want to find its area as a simplified polynomial function. So it's x plus 3 times x minus 1. All right, so we can do that by saying x plus 3 times x minus 1. And I can use my distributive property that's going to give me 4 terms. X times x is x squared. X times negative 1 is negative x. 3 times x is 3x, and 3 times negative 1 is negative 3. And I can collect those 2 like terms in the middle to get x squared plus 2x minus 3. Okay, that wasn't too bad. I can also do the box method, and I can literally kind of do it over here on the box. I just break it into 2 pieces like this. This side was x plus 3, and this side's x minus 1. So the 4 areas are x squared minus x, 3x, and minus 3. And you'll notice that the diagonals tend to be the same terms, or like terms. So from that, we could have easily seen that it's, oops, wrong tool, x squared plus 2x minus 3. Which again is exactly the same as we got when we did it algebraically. Now this one, the box method still works, even though the shape that we're dealing with is actually a circle. So algebraically, I get 3x, the area to be precise here, equals pi r squared for a circle, which is pi times 3x minus 4 squared. The pi I'm just going to leave out for a second because according to BEDMAS I have to do the power before I do the multiplication. So that'll be 3x minus 4 times 3x minus 4. That times that, that times that, that times that, that times that. And that'll give us 9x squared minus 12x minus another 12x plus 16. Collect those middle 2 terms to get negative 24x. And then if you want at this point, you can expand out and put the pi into each of the terms. So that would be 9 pi x squared minus 24 pi x plus 16 pi. Again, if you prefer to use the box method for the multiplication, oops, 3x minus 4, 3x minus 4 gives you 9x squared minus 12x plus 16. Exact same idea, just helping make sure that we don't miss any terms or add up any terms that aren't there. That's really about it for this lesson. Again, as same with all the other lessons, practice problems at the bottom, give them a shot, check the answers. If you're getting them right, fantastic. And if you're not, let me know and I will do my best to help you out. We'll see you in lesson 3.